Hello folks, how's everybody? I hope you're doing fine today. Want to remind everyone that we have a conference coming up in the 4th of April. Okay, that's going to be in Lusaka, Zambia. So if you plan to go, get your bags ready and buy your tickets. Okay, make your reservations. Second thing I want to remind people of, we have a book, was uploaded the other day. You can download it for free, okay? And it brings you up to speed on the rope hypothesis. And one of the things we're asking people, whoever has a different language, has another mother tongue or whatever, mother language, and wishes to translate it to his or her mother tongue, to contact us at tokakaka@hotmail.com. And what we can do is send you a Word file, and you play around with it, and then send it back, and you can send it back as a PDF file or send it back as a Word file, and we'll upload it and give you credit for it, okay? Okay, so having said that, let's get on with the subject matter today. It's going to be about infinity. What is infinity? And before we can get there, as an introduction, I have a couple of comments that I want to address, okay? And I think they're important comments, both of them, so here goes the first one. If I can get it up there. There it is. This gentleman says, since only objects can have location, why can't an object then just be defined as that which has location? Sounds reasonable. For example, the triangle is a shape, but is also a concept and not an object because it has no location. Okay? On the other hand, if the definition were that which has location, it would still be an object and it exists because it has location, whereas the concept does not exist. This way, anything without location is a concept, and anything with location is an object. Thus, you eliminate the mention of shape altogether. Sounds reasonable? Well, not to me. Okay, so let's see why it's not reasonable, why it's unreasonable. Okay, so let's look at that. In the foundations of physics, we have to maintain a certain order of definitions. You can't just define words in any old way. You can't put matter, for example, first and start defining matter and then work your way towards exist or whatever. Or you can't put exist first or motion first, especially motion. Now you have to define them in this order, this specific order. Not only are these words sine qua non, you absolutely need to define these words in physics, which no one has in the last 3,000 years, but you have to define them in that order. See, I can't put location as a criterion because we haven't defined location yet. I can't talk about location until I first put an object in the location. Remember, physics is first and foremost the study of objects, okay? So we need to define the word object first and foremost. That's the first word you need to define in physics. You can't avoid it. The idea is you can't do physics without an object. If there's nothing in the universe, you can't do physics. There's nothing to study. Assuming you were the only object, just the eyes, your mind, or whatever, or your God, when you're looking out there, there's nothing, absolutely nothing. What physics is occurring, what phenomenon is occurring. So the first thing you need to define is the word object. You need to know what an object is in physics because you can't do physics without objects. Once you define an object, then you can define the other words. You can define distance because that's the separation between two objects. Location is the set of distances. I screwed up there. It's a set of distances, okay? That means you need the object first, then you need to have the location. Okay, motion, two or more locations of an object, etc., etc. So you need the word object before you can do any of those words. That's one issue. Here's the other issue, and the other issue is that why we chose shape, and that's because it's the only universal property, attribute that all objects have. Okay? All objects have shape. See, touch invokes another object. Mass invokes another object. Mass is a dynamic word. Some people think it's the quantity of matter. That's what they've been taught in high school. Well, that's been overthrown. So if that's the idea you have, you better do some research, because that's not the definition of mass. And anyways, mass is something you determine through weight. We measure in kilograms, we put it on a scale, so it's a dynamic concept in that sense. Volume, same thing. It's the region occupied by an object, etc., etc. All those are either require another object. That means you got a circular definition. You need an object to define an object. Okay, you need two objects in most cases. Others think it's just the subject of a sentence, etc., something you can talk about. There's different notions of what object is. The only one applicable is shape. And that's why location doesn't cut it. And the other thing about location is that, not all objects have location, as he well said. There are objects like triangles which have shape but no location. And so we just say that those are objects that do not exist, because exist is object plus location. Okay? You need to have location in order to exist. So if God wants to exist, he knows what he's got to do. He's got to not only be an object, he can't be love or intelligence, he's got to have location as well with respect to the remaining matter in the universe. And people try to put them beyond your mind, and they put them on the fourth dimension or the fifth dimension or the 26th dimension. Well, God's outside of the universe. I don't care. You put him anywhere you want. There's got to be a straight line from God to me, no matter what. He can't escape that straight line no matter where he stands in the universe. And you can go on and discuss on your own, but that's the argument. The argument is there's a straight line from God to me, and if there is, then he exists. And if there is no distance between his chest and mine, God does not exist, period, by definition, not because I believe or don't believe or whatever. Okay, so here's a second comment which I want to address, and which deals with the subject matter of today. It's got to do with infinity. Visitor says, infinity is a valid mathematical concept, okay? It indicates mathematical sequences that have no hard stop, okay? Okay, take a sequence such as all the natural numbers. You can list lots of them, but at some point you have to stop, right? You count to 100, you get tired, that's all you did all day, 8 hours, you counted to 100. Well, you can go to 101, but you stopped at 100 and you know that the numbers continue. That's what he's saying here, okay? You can list lots of them, but at some point you have to stop. But no matter which number you stopped at, there is the potential to have identified more natural numbers. The natural numbers do not run out just because you stop listing them, okay? Okay? What infinity validly indicates is the potential to progress in sequences no matter where you stop. In that case, lots of sequences are infinite. Infinity merely indicates that when progressing in some sequences, you have to stop at some point. But the sequence does not run out of terms. You have to have you had kept going. If if you had kept going, you could have found more terms. And he says it has a place in science, at least in the science of mathematics. So the first issue I want to address is that last one. Okay, mathematics is not a science. Mathematics has nothing at all to do with science. Let's get that straight up front, okay? People think that math has something to do with physics, with science, that it is a science in itself. No, it's not a science, okay? Math is a language. Is Chinese a science? Is Russian science, the languages? Are those sciences? No, they're just languages. And mathematics is a quantitative language of adverbs, exclusively of adverbs, quantitative adverbs. It doesn't deal with adjectives. It doesn't deal with objects, even though it talks about mathematical objects. No, they're not objects, not for the purposes of reality, physics, etc. So mathematics is a quantitative language. It's a language of quantitative adverbs. It only describes motion or qualifies motion or modifies motion. That's all it does. That's all that mathematics does. It doesn't do anything else. Take any equation, all it's doing is describing some kind of motion of entry. That's what it is. It's giving you the location of a point or a value. That's all it is. And so what happens? You can't have mathematics be a science because it's just a language. That's the first issue. The second issue, mathematics is a language that can only describe. And science is not about describing. Science is about explaining. That's where we differ, okay? Especially with a mathematical establishment. So here's the scientific definition of science, okay? And here you have it in comparison. It's rational explanations. Okay, and physics is the rational explanations of phenomena, and we require objects because we're going to explain causes and mechanisms. And where do we put, not math, because math is a language, where we put irrational theories is under religion, and that includes all of mathematical physics. Everything done since the Greeks to today, to Stephen Hawking and beyond. Mathematical physics only has irrational explanations for the everyday phenomena. You know, the moon going around the earth going around the sun, they tell you it's warp space. Then they tell you in quantum mechanics, on the world of the small, that a particle can be at two places at once. All those are irrational theories. I don't care how they want to twist it and turn it, they're irrational theories and they belong in religion. So that's where we put all of mathematical physics. Not mathematics. Mathematics is a language of symbols, okay, of adverbs. That's one thing. The conclusions, the physical interpretations that the mathematicians derive from their equations, which they purport to explain causes and mechanisms of how this universe actually works, that's where we get into irrationality. That's what we attack here. Okay, we're not interested in math. We're interested in attacking the physical interpretations of mathematical physics, specifically of quantum mechanics and general relativity. Okay, and all we have to look at is some of the definitions that we looked at the other day that we find out there for science, and we find out that there is no definition of the word science as of today, not an official one. They have all these things that we discussed the other day. I'm not going to go over that again, but just quickly, it's not a study, and one source says observation experiment, the other one says testable explanations and predictions. So they have all these notions and nobody knows what it is. It's like science is everything. They never had a definition of the word science, and that's why we're in a mess today. And you know, this gentleman who wrote, he's got to begin there. He can't escape the word science, can't say, well, this is what we always thought about science, this is what we were told, and this is, you know, this is like saying that, you know, Christianity is correct because, you know, 90% of the world believes in it, or maybe 90, I'm a little over there, maybe 30% or whatever of the world believes in Christianity or in God and whatever. Should we accept that simply because most people believe in it? Is this a democratic type of thing where we all raise our hands and vote? Is that how we decide what science is? No, you have to fight for your definitions. That's how you do it. And if you don't have a rational definition like no one has today for the word science, that's where we should start. We can't skip that step. That's the starting point. You need to define science. Okay, so right now we don't have a definition of science. I've defined it, rational explanations. Very simple. You don't like it? Give me a definition to oppose it, to contrast against that, and see if you can defend it. And I'm sure you're going to have a tough time. You're just going to be defending your religion. Okay? And just in case, physics, right? We have good old Aristotle's definition. Okay, we went over that the other day, but let's go over it real quickly. What does physics means? Essentially the study of nature. That's what the word physics essentially meant, or somewhere along those lines. Maybe the translation is not perfect. Who knows? But what was it? What was he referring to? Of things that exist. Yeah, that's physics. Physics deals with what exists out there and what happens out there. That's what you got to explain. Nothing to do at all with mathematics. Mathematics has no business entering physics because math cannot explain what exists. Okay, so that's where the problem comes. And so, and yeah, it's the study of nature, and the study of nature means that we are going to figure out what exists out there, how Mother Nature does her stuff. That's what physics is. And what they did in the 17th century, they gradually, from that point on specifically, it already came before then, but from that point on specifically, they started drifting more and more into mathematics, into abstractions, and they ended up with the nonsense of quantum mechanics and general relativity. And what is the problem with that? The problem with that is that they say, well, we ran a test. We didn't see because we can't see these invisible things. And these are the conclusions we have. But see, the problem is they simulated whatever they saw, whatever they didn't see, they simulate everything with particles. That's the problem. The problem is particles. The particle hypothesis has to die. We can't explain a single phenomena in the universe with particles. And it's the particle people who are in the way. They should get out of science. They have no place in science anymore. If you haven't figured out after 10,000 years that you cannot explain a single phenomena of nature with particles, then you got a problem. Yeah, you need to see a psychiatrist. That's what I think. I mean, you got the force of pull and they can't explain it with particles, so what they do, they explain it through pressure. You remove whatever's between two objects and the particles on the outside push them in, or something along those lines. Quantum mechanics has it even more more abstract. They say, one object throws negative motion, negative momentum to another, and that's how it draws it. You send negative motion, and instead of hitting you and pushing you away, it draws you in because it's got negative motion. All you do is put a negative sign in your equation and you're done. But the question is whether they can do that in a lab. They can show that negative sign in the lab. Okay, so what's the subject matter today? It's infinity, just like this introduction we just had. And we started last week with good old Aristotle and Euclid. Euclid came a little later than Aristotle. He was the next generation, but they were working on two different things. Aristotle was working on physics. He was trying to figure out, motion, time. He was analyzing distance, those sort of things. Euclid, he was working on different kinds of nouns. He was working on geometry, and so even, they had these differences. They applied all these adjectives and qualifiers and adverbs to different nouns, to different situations, to a different realm, okay? But what they both used is the notion of infinity, and that was quite prominent among the Greeks. They all dabbled in infinity. And one of the issues was, whether the universe was infinity, whether what was beyond Mount Olympus, the gods out there, whether that was infinite, so, the ether, not only the quantity of particles, but the ether as a volume, was it infinite? These questions popped in their minds, and since it was beyond their capability of understanding all that, they just said infinite. So what is infinite? Infinite is infinity. Infinity is an adjective that the mathematicians have converted into a noun. That's what it is. They morphed it into a noun. So, you have an infinite series, and you go to the end of the series if you can, or just keep going, and wherever you are, that's infinity. That's aware. That's what infinity is. Even if you talk about the infinite universe, infinite space, you're talking about being at the edge, of whatever's growing out there. You can't see the edge because it's infinite, right? Because otherwise you would be able to draw an object, right? And again, the word infinite is a violation of the definition of the word object. There is no object that is infinite because an object is that which has shape. And now we do have a problem with the word infinite because infinite is an oxymoron. You're saying that the object has shape, but it's infinite, meaning you can't imagine its shape. And that's where the contradiction comes with the word infinite. It should never be used in science. Infinite only belongs to mathematics, and the context is what? Numbers. But it goes a little beyond that, and that's what we're going to look at. Here we have Euclid's notion of infinity. He puts it in elements, Okay, and you go in there and you look at the Proposition 20 in Book 9, he says prime numbers are more than any assigned multitude of prime numbers. And that's the notion of this, what this fellow said earlier. He said the sequence does not run out of terms. If you had kept going, you could have found more terms. In other words, you can always add 1 to whatever number that you ended up with, and you can continue adding 1 and 1 and 1 and 1 and 1, never end. Okay, the integers is one of the so-called infinite series. And so this is what Euclid was referring to. And as we'll see in a minute with Aristotle, it's known as potential infinity. Okay? And another notion, a little unrelated, but more related to what Euclid was trying to explain out there, it has to do with this, with the fact that he defined a line, for example, as an infinite geometric figure, if you can think of it like that. I mean, I can't imagine how any geometric figure being that which has shape, synonym of object, how it can be infinite. But here's one of the objects that he made infinite, okay? And he just made the line grow. And he needed that because when he had a triangle, for example, and he wanted to calculate an angle, what he did, he would just extend the line and look at the angle on the outside. That's how he figured out a lot of these things. That's how the Greeks handled these situations. They looked at angles outside of the triangle to figure out things about the inside of a triangle. Okay, and so he says in his Proposition 12 in his Book 1, he says to draw a straight line perpendicular to a given infinite straight line from a given point on it. Okay. The Greeks, just like we have today, they had this notion that a line was infinite. See, the line they always draw for you on the board, I've never seen an infinite line. You know, not a teacher has ever drawn an infinite line for me. It's always a line segment, what is known as a line segment. And so what the Greeks did, they made their line infinite, okay? In other words, it just kept going and going and going, whatever that means, because, you know, it's like, well, I mean, where does it stop? Is it a geometric figure? How do you know it's a line if you haven't seen the whole thing? See, a line segment, you see the whole thing. You say, okay, that's a line, which is really a line segment formally, right? But when you look at an infinite line, one that is, I guess, growing, or God is putting more points ever at the end of it in either direction, well, then what sense does it make? What is that? How do you know it's a line? Because you haven't gone to the edge, to the border, to the end. So you can't, and for sure that doesn't qualify as a geometric figure, because a figure is that which has boundaries. Okay? And so we got a contradiction there. And, you know, that's the foundation of geometry laid down by the Greeks, and it's what we learn by rote in school these days. And that's what all these mathematicians, that's what they subscribe to. So you talk to them and they say, oh yeah, the infinite line, and for them it's just no problem. It's like, it doesn't matter to them, right? Okay, Aristotle, he applied infinity to a different set of topics, okay? He was into something else. He was trying to explain, at least primarily in physics, but also in metaphysics, his other book, if they're his. Maybe they just came from his students at the Lyceum. But he applied it to shape and form, number of existence, one of the things, you know, like even assuming the ether is made out of particles, right? Let's assume that for a second. How many particles are there? Is it infinite? An infinite number? You know, I mean, how many? Do we count all these particles and say, well, there's a billion, a quadrillion, a gazillion? And you know, if it's gazillion, you got a fixed number, you know, whatever, one with a bunch of zeros. But if it's infinite, then those zeros keep adding up. Okay, so you got to determine whether the number of existence is fixed. Okay, so this is what he applied the notion of infinity to. This is what he's going to be talking about, what he's going to be arguing for. He's going to justify it. Okay. Obviously, he applied it to numbers. He applied it to the heavens. You know, is space infinite? You know, is space, the universe, are the heavens infinite? And here we have a little problem with that because, you know, you're treating space as a physical object, or the universe, if you will. Let's look at space first. You're treating space as a volume, as a box, as a balloon, any way you imagine it. You're treating it as a body of water, the cosmic ocean, as Sagan used to say. Is space a physical entity? And if it's a physical entity, you have to tell me what's on the outside. You have to label that on the outside. And no, you don't have to go to the edge of space for that. No, this is a conceptual issue. You got to drink a beer, sit back, and just visualize it for me and label it. Tell me what's outside of space, what gives contour to space. And this is where Aristotle, you know, more or less had a problem, right? Because they kind of said, well, it's infinite, and they just left it at that. And, you know, like, let's not talk about it because there's, like they say today, we have no way of proving it. You know, we have no way of going out there and finding out what's on the outside of space. And so they made space infinite and they solved the problem. You know, it's infinite. So no more questions. Okay, that's how they handled it, and that's how they still handle it today. And no, this is a conceptual issue because if space is, as we say, nothing, then space, in which nothing is the opposite of something. Something is that which has shape. Nothing is that which doesn't. Now we can use the terms consistently because they are antonyms. They are opposites. And so if space is nothing, then space cannot be infinite. Even if it were an object. If it were an object, you have no infinite object. And if it's not an object, you cannot talk about an infinite concept, not in physical terms. So it doesn't make sense to say that space is infinite. Or the universe. The universe creates its second problem because now we're talking about also, you know, the number of existence. In other words, let's assume there are particles out there. Okay, not only planets and gases and whatever is out there that we can see, but also that which we can't see. Let's say space is made out of particles, as the etherists essentially are saying. So the question there is, again, are those particles infinite? In other words, do they stretch forever? And this is not an issue of going out there and proving it with an experiment. This is, again, a conceptual issue. If you say that it's infinite, okay, then it's not an object because all objects have shape. You should be able to draw space if space is finite. If it's infinite, it contradicts the definition of object. And if it's finite, you got to tell me what's on the outside of it. You got to label that. What is it? Thought that encompasses and encapsulates space. So these are the issues. You got to resolve that because these are conceptual issues. You don't go out there and prove it with your rocket because before you do before you do an experiment, you got to do a design of experiment. You got to conceptualize it on the board. That's the issue. And so, yeah, the issue is whether the heavens, these are the topics at which he applied infinity to, or the notion of infinity. Motion. Is motion infinite? Is time infinite? You know, what do we mean by these things? And here you have an example from Aristotle's book where he used these notions. The notion applied, the infinity applied in regards to time and in regards to time, to motion and time. Since everything that is in motion must be moved by something, he always had this prime mover idea in the back of his mind, right? Let us take the case in which a thing is in locomotion and is moved by something that it is itself in motion. And that again is moved by something else that is in motion, and that by something else, and so on and continuing. Then the series cannot go on to infinity, but there must be some first movement. Okay? In other words, he's saying he's going to analyze whether motion is infinite and whether you need a mover, because if the original mover, we'll call it the alpha, okay, that's the guy or whatever that set things in motion, because until then there was no motion, he's asking what moved him. But even assuming that he had no need for something to move him or it, right? Then the question is, then you don't have infinity in that direction. You have a starting point. Okay, so you got to look at these because these are conceptual issues. Okay. The other topic he applied it to is time. He said, let us further take the time in which A has completed its motion and let it be represented by K. Then since the motion of A is finite, the time will also be finite. But since the movements and the things moved are infinite, the motion EZHO, in other words, the motion that is composed of all the individual motions, must be infinite. So this is what he was talking about, nothing related to geometry as in the case of Euclid. Okay. Now, why did Airy bring these things up? Well, what was he after? Okay, that's what you got to look at the context here. Okay, and he wanted to attack or challenge the notions by the Eleatics. Okay. Let me get to that in a second. Let me first say that what Airy did as a result of this, he applied infinity to several concepts, as we just discussed, but the issue is he came up with two notions. One is the potential infinity, which is what this other fellow just discussed, and the other one, which is a little harder to understand, which is the actual infinity. And potential infinity is pretty easy to grasp. Okay, if you can add another number, then you'll just be counting forever. I call it incessant counting. Okay, counting numbers incessantly. But the other notion, which is a little more difficult to grasp and which very few people really talk about, is this other notion that Airy had, which is actual infinity. What does he mean by actual infinity? Well, here you have a Venn diagram, for those of you who are familiar with that, and you're going to put the integers in there. So by definition, the integers are a complete system. Okay, so within that system, he says, there is an actual infinity, but it's not real in the sense that, you can't go to the last number, that sort of thing. And to understand this concept a little better, what I did was put a different example, which I think is going to put it in a better light for you. And this is my example, okay? Let me put it over here and get rid of good old Airy here. Okay? And what is it? It goes like this. Imagine you have a line segment. Not a line, not the infinite line. We're talking about a line segment. So what does that mean? It means that you got a fixed line. And we're talking about geometric line. We're going to consider it one-dimensional, whatever they want. Okay, it doesn't matter. We got a line, and a line segment. Sorry, and the question is, that's a complete system because you got the whole system within the Venn diagram. So it's all there. All that I'm going to talk about is the line segment. It's already there, completed from A to B, from one end to the other. So you got the complete system there. Now I ask you, how many locations are there on that line? How many points? Points is a location, right? That sort of thing. And now you have an infinite number of locations, to use that term, okay? In other words, you can count incessantly all the locations, and between any two locations, there's another location, and between any other two, there's another location. So you have an infinite, to use their term, right, set of locations for a fixed system, for a completed system. That's the notion of actual infinity, okay, that these people are trying to get to you. So I hope that helps you visualize a little bit of what they mean when they say actual infinity. Okay? Okay, so Airy used this to attack the Eleatics. Why? Because the Eleatics were said there is no motion. Motion is an illusion. There is no such thing as motion. You say, whoa, what are you saying? Yeah, that's what Parmenides and Zeno, probably the most famous of the Eleatics, said. There is no such thing as motion. Motion is an illusion. Okay? And I showed this in a previous lecture, in which we had Democritus and his atomists, and he believed there was motion. He said there is motion, you move, and I do it with the 15 or 16 square puzzle, right? And he said, yeah, there is motion. See, you move one and another one moves in that later in that place, okay? And so there is motion because there is a space in which something can move. The Eleatics said, there is no such thing as free space. And so they said, there is no way that you can move one of these little numbers to a space because there is no open space. And Aristotle and people like Descartes, who followed him in this notion, said, yeah, there is space, but see, it's immediately taken up by another square. Okay, so this was their differences in the way they perceived motion. This is what they were going to talk about. Okay, so we have the Eleatics, and they said there is no such thing as motion. And Aristotle said, you guys are wrong. There is motion, except that something fills that space immediately. And this was used by people like Descartes, Thomas Hobbes. We're talking about 17th century here. Thomas Hobbes. Who else? Descartes, Thomas Hobbes, a few others. Don't come to mind right now. But they criticized this notion that Torricelli had, that he said he created a vacuum. Okay, and I showed that the other day, where people like Robert Boyle and Guericke, the German guy who created vacuum there in his double hemisphere, copper double hemisphere, they created this thing which they said was vacuum, and which was the top. In this case, in the case of Torricelli, the top part of the little test tube there, the upside down test tube, okay? And they said, look, that little space up there, that's vacuum, okay? And that's why the water can't continue flowing up there, because it's stopped by vacuum. And what people like Descartes and Thomas Hobbes, who followed Aristotle in this sense, they said, no, something fills that space. You're being fooled. You're deluded. Because, yeah, you remove the real matter, let's assume air, water, whatever, from that area, from that volume. But through the interstices of the crystal structures or whatever that you had in there, you have ether flowing in. So you have the ether filling in that vacuum, and you never have total vacuum. You have all these little particles that we can't see. They called it ether, and they say, well, that's filling the vacuum. And so this was an issue. This was an issue whether there is motion, whether and whether there are infinite particles, and if we're swamped by particles, as soon as you remove the visible or big particles, the little particles fill in the space. These were the issues that these people discussed intergenerationally. Okay. So where do we go from here? Well, here's the most famous of Zeno's paradoxes. I guess a lot of you heard of them, the Achilles and the tortoise. And what it is that, Zeno runs half, the tortoise has, say, 100-meter advantage over Achilles. So in order for the Achilles to catch up with the turtle, according to Zeno, he had to run first half of the way. And by this time, the turtle went a little further, maybe 2 more meters. Then Achilles had to run half that distance, the 50 meters plus the 2. Now he's got to run 26 meters. Okay, so now the turtle goes another 1 meter, and now he's got Achilles has to run half that distance, and so on. So Achilles never reaches the turtle. That was Zeno's point. And from this, he tried to prove that there was no motion. That was the idea that the Eleatics had. And another notion, another paradox from Zeno, which is probably just as famous, is the flying arrow. And this is how it was handled. Aristotle talks about it in his book Physics. Okay, now book 6. Says the flying arrow, Zeno's argument, and I summarize this, okay? There is no motion within an instant of time, right? Time is comprised of instants, right? We have all these instants, and there is no motion in one of those instants, therefore there is no motion. Because if you take no motion, no motion, no motion, no motion, you get the series of no motions, well, you end up with no motion. That was Zeno's argument. Okay, so what does Aristotle say to that? He challenges that notion of infinity, because again, this has to do all with infinity. They're saying if there are no spaces, they're not infinite spaces to fill, then there is no motion. That was the Eleatics. And Aristotle says, no, the flying arrow is at rest, which result follows from the assumption that time is composed of moments. Okay? If this assumption is not granted, the conclusion will not follow. Okay? So he's saying, is time composed of moments? This is what Aristotle is challenging. So he's saying if time is not made of motions, then Zeno's paradox dies right there. Okay, that's it. That's his argument. What is my argument? Rational physics argument. We have a better argument. Okay, and we throw what Aristotle say down the drain. We say, look, motion, two or more locations. Location is a static concept. Okay. Location can only be depicted in one frame of the universal movie, shown below, okay, just a little film strip of it. In that frame, there is no motion. So you see the arrow, and it's standing still in each one of those locations, in each one of those frames of the universal movies, in each cross-section of time, so to speak, which cannot be, or you can call it a moment if you want, no problem. You can call it whatever you want, but my point is, but you can't really call it an instant, because an instant of time requires more than one frame, no matter what. Time requires at least two frames, same as motion. Motion requires two frames. And so what they're confused here is the notion of location. Location is a static concept, and you can think of location as a photograph, and motion and time as a movie. So the arrow is static, is standing still in each one of those frames. Okay, so there is no motion within the frame. In order to see the arrow move, you got to see the movie. You got to watch the entire movie. You got to have more than one frame of the universal movie, and that's our counter argument to Zeno's paradox and what Aristotle proposed, which is essentially what the mathematicians today argue. So here we have some of the notions that infinity have, some of the mathematicians developed notions of infinity to ridiculous levels. And one of the prime guys for that was Georg Cantor. He was a German mathematician, spent, I guess, half his life in a loony asylum, and you'll see why, because he just overworked his head on this issue of infinity, nonsense that mathematicians worry about, which has no bearing whatsoever in science. Okay, and what George, I guess, he identified three types of infinity. He says the infinity of God. And again, the issue there is whether God is a physical object, and he's saying that he's so bloated that you can't see the edges of God. I don't know what he means by infinity of God. Are we talking about God's omniscience, his intelligence? Are we talking about, or knowledge? Are we talking about him being everywhere? What are we talking about when we say God is infinite? Well, what sense does that make? Are we saying that God himself is infinite? We live in his stomach or something? I mean, what is this? The infinity of reality. Okay, and there he tried to give the notion that the items in nature, the like the elements that we talked about a little while ago, the elements, he said, could be infinite because there are other worlds out there and they have elements as well, and so I guess he saw the universe as never ending, and so there's all kinds of matter out there, and all of that is simply uncountable, and therefore it is infinite, the infinity of reality. That was, I guess, his notion. And then the other one, which is the one he invented, is the transfinite numbers and sets of mathematics. He didn't like to call, I guess he didn't like to call it infinite, so he called it transfinite. He's the first guy to invent trans. And so he came up with the transfinite cardinals used to quantify the size of an infinite set, and transfinite ordinals used to provide an ordering of infinite sets. None of that has any bearing on science, on physics. I don't know why he wasted his time. Uh, the way we look at it in science, in rational science, there's really three notions or three applications for infinity, at least three. Maybe there's some other. And here you'll see them. I synthesize them. The adjective infinite morphed into noun, the noun infinity, okay, becomes a place somewhere, okay? So we have no use for it in science or in physics at all. The word infinite should be wiped out from the history books, from science, from everywhere. Keep it within math if they have any use for it, okay? Counting incessantly. You count, that's more or less the notion of this potential infinity. You just count, and when you get tired, you know you're going to continue counting tomorrow because that's your job, to count numbers. Okay, so you keep counting and take off where you left the day before, and you count incessantly. That's one notion, okay, of infinity, and again, that's applicable solely to math, has nothing at all to do with physics. Okay, there's no real physical purpose for the word infinite or infinity. Moving constantly. This is a different type of notion, somewhat related, because counting incessantly, you're doing motion as well, right? But here we're talking about moving, motion. You're not counting, you're just moving. And it's known as perpetual motion. And the question is whether there is perpetual motion. Under the rope model, we say there is perpetual motion. There's only one perpetual motion, and that's the universe. Okay, there's a single thread that underlies all matter, and this thread is eternal in both directions of time. It never had a beginning. It was never created. It will never die or stop moving. And so the universe, if we're going to use that term, it's a concept, but the universe is a closed system. Space, which is nothing, and matter, which cannot cross the line of that which doesn't have a line, which doesn't have a border. So matter has no way of escaping space because there is no border to escape. Not even God can escape that which has no borders. Okay? So space does not allow matter to leave because there is no such thing as space. That's why. It's not an enclosure. It's not a container that you can reach the edge and see how can I get to the other side. No such thing. Space does not exist. There is no such thing as space. Space is nothing. And we have this matter, which is a single thread that underlies all of the universe, and it's just floating there with respect to each other. Atoms with respect to atoms, all made by this single thread. Okay? That's the notion. Okay? And so this moves on forever. When we die, when we're gone, the universe will continue, all this matter in the universe will continue moving. So in that sense, it's perpetual motion, not because it was set in motion at some point in time, but because something we cannot imagine, and that's that just like matter had no moment of creation, motion had no kickstart. It never started moving, and people have trouble with that noise. It drives them nuts because they say, "Oh, what are you saying?" Yeah, because we're not used to it. It's not part of our ordinary experience. But yeah, that's what we're proposing. We're proposing that, I hate to say it because my son doesn't like that notion, it drives him nuts, but there were people before us in the universe. You know, we're not the first humans to appear, or life forms for that matter, to appear on Earth, in the universe. There were living things in other planets gazillions of years ago. And before them, there were people before them gazillions of years ago. And before them, there were people before them gazillions of years ago as well. So there was no first human, there was no first life form. And that's hard for people to grasp. They say, well, what do you mean? There was no starting point, no starting line where everything got set into motion, where objects were created and suddenly started moving? No. Okay, so this is a difficult concept to grasp. So let me say it again. There's a single thread. This thread has moved on forever. It was not created, neither was the motion with which it started. Okay? If God wants to be part of that thing, he's got to be made out of atoms. He's got to be made of that thread. Otherwise, he's not here. Okay? And people have a lot of trouble with that because there is no room for God in the single thread. God is not even outside of that because, you know, he would still have distance with respect to me or location. No. If God wants to exist, he's got to be part of the universe. That's the only way we can use the word God exists consistently. Anyways, that's food for thought for you there. The other one is the third notion of infinity is extending a line forever. That's the notion, again, of mathematics, geometry in this case, and they cheat because, again, it's a question of definition. What is a line? Is a line distance? Is the line representing motion? Is it representing time? What are you representing with this so-called line that is infinite, that it stretches in both directions? What are you talking about? Are you talking about geometric figure? If it's a figure, it better be at least two-dimensional. Line is said to be one-dimensional. So I can't even draw it. I drew a two-dimensional line, a plane, that's what I drew. And it continues eternally if it grows, which is the notion that geometry wants to give you, you know, that the line extends and nobody asks any questions. And what are we talking about? What is this line, this magical line? What are we saying? We're projecting a line just to get an angle, just to prove a theorem? Is that the purpose of doing this? And again, all that can stay within geometry. If they want to play around with that, with this abstraction, that's fine, but keep it within geometry. Don't tell me it's got something to do with the real world out there. The real world, we have to explain mechanisms, causes. And what all these people do with their infinity and their geometric figures is talk about an abstraction just to visualize relations. That's it. It's got nothing to do with explaining gravity, for example, or electricity or whatever. So all these abstract concepts should stay within math, and that's where infinity belongs, in math. They can talk about the infinite series of numbers, that's fine. As long as they keep it there, it's fine. It's when they bring it into the real world and say that space is infinite, the universe is infinite, my love is infinite, that's when we get into trouble because we're using the word in the wrong place. You know, we're using it to apply it to concepts. And concepts you can't use an adjective to qualify a concept, not in physics. Maybe in ordinary speech you can, but not in physics. In physics, you can only apply adjectives to objects. So if you're going to use the word infinite, you're going to have to apply it to an object, and there is no object that is infinite. That kills the word infinite for the purposes of physics and science. Anyways, I'm going to continue analyzing a little bit of Aristotle and Euclid, and we're going to get into lines, and from lines, to planes. We're going to fly, okay? So we'll see you on Sunday, and hopefully you'll come back. We'll see you then. Bye-bye.